Okay, so I'm going to start now. Good afternoon, everybody. We're going to have our second class about exegetic analysis today. I told you last week that we're going to have 3 classes on exergy analysis. And well, the first one was more focused on the fundamental aspects of this kind of theory of exegetic analysis. This second one, I'm going to start to apply these ideas and these tools to a separation process. And next week or the next class, we're going to finally try to calculate how much energy is necessary to recompose the constitution of our atmosphere. Okay, so today we're going to talk about the thermodynamics of a separation process. It's a very important issue, and as I'm promising since last week, we're focusing on this type of problem. Building a CCS machine, a carbon capture and storage machine, which is driven by sun energy. And this machine will remove CO2 from our atmosphere, today's atmosphere, in order to render the constitution of our atmosphere at least to that one before the Industrial Revolution. Okay, so I intend to calculate how much energy or organized energy, exergy, is necessary to reconstitute Earth's atmosphere to its original composition prior to the Industrial Revolution. Okay, and the tool for doing this is exergy analysis. And since it is a separation process, that's why I'm focusing on separation processes today. Okay, so talking about separation processes, I think this is one of the most important processes in industry. Roughly speaking, it corresponds to 40 to 90% of total costs. Just for you to have an idea of how much it is, you can think about, for instance, our fuels, fuel for transportation sector, gasoline, diesel, kerosene, and so on. Except for electricity and other liquids on top here, everything is from petroleum or, well, natural gas. You also have to make some separation, but petroleum will help producing gas, liquefied petroleum gas, gasoline, naphtha, and so on. And this is actually a separation process. And I just put a picture here for you to have an idea of the size of the equipment which is devoted to this kind of process, separation. So in addition to being very widespread applied, these processes correspond to a high percentage of the total costs, including CapEx and OpEx. Okay, so our motivation is, I'm going back one slide, since separation processes are very, very, very important and they consume exergy, what would be the minimum amount of work or organized energy necessary for the separation of the components of a given mixture? Okay, so we're going to elaborate on this subject today, so that next time we meet, we are going to analyze Earth's atmosphere. Okay, so that's our motivation for today, calculating the minimum amount of work for a separation process. And well, separation process, when we say like this, it's misleading, kind of misleading. It's very, very, very widespread applied. So, okay, you can imagine, for instance, our sugarcane harvesting process. It can also be seen as a separation process. As you know, the harvesting machine today, that's today's technology. Okay, it harvests, it cuts the stalk here near the soil, and there is a pneumatic separation process. So the stalks are collected here in this wagon, and on the side here is tops and leaves, what we call palha, okay, in Portuguese. And the idea is to not only to use the stalks for sugar, ethanol, and electricity, but also to use this lignocellulosic material. Well, you can burn to generate electricity, but you can also use it as a chemical compound, okay? So what we're doing here is already we're separating, because tops and leaves and the stalks were mixed down here, and now they are separated here, okay? You see it with your own eyes. And the problem is that if we want to use these residues, they are not residue, okay, they are feedstock actually, but if you want to use them, since you have already separated and they are left on the soil, you have to get it back. So what do you have to do? As I was saying, the stalks which were collected on these wagons follow the traditional processing path, okay, so preparation, extraction, and so on, and you can make ethanol and sugar, for instance, okay. So that's the traditional, what we've been doing since the 70s here in Brazil, or even before that. If you want to collect thrash here, tops and leaves, straw, okay, you have several agricultural operations. First, you have a tedding operation. You need to build these piles here. Then the baler comes and eats these piles and build the bales. Then you have to pick and stack and handling, put all these bales in a truck, and then you take that to the industry, okay? Straw. To follow a thermochemical processing pathway or a second generation processing pathway, okay? So that is how things are being done today, but from the point of view of exergetic efficiency, it's very, very nonsensical, okay? Why is that? Because, well, they were already together, I mean stalks and straw. They were separated and then spread over the fields. Then you have to collect that to make the bales and then transport the bales to the industry. And I'm not showing, but you have a machine here to unbuild these bales, okay? So it's nonsensical from an energy point of view. A better system would be something like this, okay? What we call whole harvesting technique, colheita integral in Portuguese, okay? So if you can, because this is not always possible, but if you can harvest everything together, stalks and straw, you put everybody in a truck and you go directly to the industry and then you separate. If you do this, there's a lot of advantages. You don't have to transport to embark a separator in this machine, okay? This is actually a giant grass cutter, okay? Long cutter. And so it's a very simple machine. And well, what's interesting here also is that you can go directly with the truck on the fields. You don't have to worry about soil compaction. So if you can do this, it's a lot better. But to be able to do this, as I was saying, you have to have a special kind of plants that accept these heavy vehicles on top of them, okay? Also, you have to have a very efficient and robust separation process, stationary separation process. So we're going to do some calculations on these strategies, but I have to make the theory before that, okay? So let's think from a more generic point of view. A separation process is something, I'm not showing what this is, what this something means, but it's something that separates, let's say, those blue dots from the golden dots here. So that's the separation process. So it can be seen as I was showing, the sugar cane, the stalks and the thrash, but it can also be garbage, for instance, as I'm showing here. You have a pile of garbage, and then you want to separate what is metallic and what is plastic residues. You have to have something here, because that's the point. This is not a natural process, okay? If you do nothing, nothing is going to happen, okay? This is not natural, so you have to have something here, okay? Why is that? Because, well, you have a high level of disorder on the left side when the components are mixed up, and on the right side you have a low level of disorder. So where the components are separated or less mixed, okay? Anyway, in order to increase the level of order or to decrease the level of disorder, you have to do something, actively do something, and, well, you can have workers which manually separate these components. So what this is something here. Does it need to expend energy? That's the point today, okay? So our machine, our separation machine, is going to be working inside there, okay? And, well, since it is a machine, it's going to demand some energy. When I say demand, well, if we make calculations and we conclude that this is negative, for instance, so it is, in addition to separating the components, it's also producing energy, okay? So that's the main idea. If I want to increase the level of order of my system, which is exactly the same as saying to decrease the level of disorder, I need to import organized energy, okay, exergy. So that's our calculation today. And this is a natural process. It occurs in nature, okay? A leaf does exactly this. It separates, it needs CO2 for the photosynthesis, okay? So it's separating CO2 from the atmosphere, and well, this is the constitution of our atmosphere, and you see that the amount of CO2 compared with nitrogen and oxygen, 79%, roughly 79%, 21%, okay, if we neglect argon, and then you have, well, 1,000 times less, you have carbon dioxide. So it's very hard to separate CO2 from the atmosphere, but the leaf does this, and the energy necessary for the separation process actually comes from the sun, okay? We know that. It also builds more complex molecules from the carbon in CO2, in atmosphere's CO2, okay? But all the energy necessary for separation and building these more complex molecules actually comes from the sun, okay? So what do we have, what laws, what tools do we have to analyze this? We know the first law of thermodynamics enforces the energy balance of the process, okay? In the absence of a nuclear reaction, there is no mass being created or destroyed, okay? So, well, energy is going to balance, okay? There's no creation of energy which is related to destruction of mass. So this is the first law. And our second law assesses the efficiency of the process, whatever it is, a separation process, okay? So, and we saw last week that combining the first and the second laws through a specific thermodynamic variable, which can be exergy, Gibbs free energy, and so on, allows us to enforce or to make these two types of analysis at the same time, roughly speaking. Okay, so that's what we're going to do in this today, in this separation process that I'm showing you. Okay, just to remember what we're calling today Exergy. Gibbs, which was one of the first to think about this problem, he called available energy. His idea was the exergy. He associated with the greatest amount of mechanical work, which can be obtained. Yeah, go on.
This is Longinus. I lost time. My video stopped working.
Oh yeah.
I don't know.
Okay, can you see it? Because it's
Yeah, it just came up now.
okay. So can I go on? Just because it's being transmitted to our internal channels, but also through my channel on YouTube. So you can watch it on YouTube if you have an internet connection. Okay. So where was I? Yeah, the ideas of Gibbs. I was trying to recover his reasoning. Okay, so he thought as energy or exergy as being the greatest amount of mechanical work, organized energy, which can be obtained from a given quantity of a certain substance in a given initial state. Okay, without increasing its total volume or allowing heat to pass to or from external bodies, except such as the close of the process are left in the initial condition. So it's a very, I'm using this sentence here because it's a very complicated idea, actually, very sophisticated idea, and we're trying to simplify today in order to apply to this separation process. That's what we did last week. Okay, so we defined useful work potential, or exergy, as being the maximum amount of mechanical energy that we can obtain from a system or from a process, okay? But the maximum, the key word here is maximum, okay? And we baptized that exergy, and I warned you that, well, several authors call this differently, okay? Available energy, exergetic energy, availability. This is a very common term, especially in the United States, okay? Reversible work and so on, okay? Well, the equation that we saw last week, we're going to apply this equation today to this separation process, okay? The exergy balance process. Our separation process can be seen as I was showing you, okay? I have a mixture of A plus B, as I'm showing you here, okay? And we want to separate A from B. We want to produce this separation. They are mixed. Well, since we want to calculate the minimum amount of work necessary for this operation, we're not going to let pressure or temperature increase. Okay, they are going to remain constant. Why is that? Because, well, if the temperature, in addition to separating, the temperature is higher here, let's say I have A at, I'm going to get my pen, I have A and B at 25 degrees, okay, 25 degrees Celsius. And if I have A at 100 degrees Celsius here, not only the energy level increased because of the separation, but also because temperature is higher, okay? So we're fixing pressure and temperature because, as I was saying, we want to calculate the minimum amount of work necessary for the separation, okay? So we're going to apply this equation to this process, a separation process occurring at constant pressure and temperature, okay? So just to remind, what are the components of our exergy balance here, okay? So this first component, this first term here, actually, if I had, because I don't have, heat being transferred to my system, Q, this heat, I know that it contains a certain amount of exergy, okay? It's not 100% exergy, it's, I don't know, 75, 50% exergy. And this amount of exergy we can calculate by multiplying it by a Carnot efficiency. Because the idea is that you take the same amount of heat, use it to drive a Carnot machine, okay? It will produce some amount of work, it will reject something to the environment, okay? And this amount of work is exactly what we're calling here exergy, okay? That's a definition of exergy. And since this is a Carnot cycle, W can be calculated as Q times Carnot's efficiency, okay? And the Carnot's efficiency, the efficiency of the Carnot cycle can be calculated from the temperatures, as I'm showing there, okay? Let me just erase here because it's becoming too polluted. Just to remember the ideas of last week, okay? So this first term here is the exergy content of any heat flux, which we are going to consider this adiabatic, so we don't have, okay? But anyway, the term is there. This other term here is, well, work, okay, being exported. And if I have deformation of the control volume surface, something like this, if I have deformation of the control volume, this deformation is compressing atmosphere, okay? So it's exporting, there's a force times displacement against atmospheric pressure. So it's trying to compress the atmosphere, and it will penalize our work here, okay? The other components are exergy associated with mass fluxes, okay? So entering, I have A and B, and exiting, I have A separated from B. We're going to have to account for this, okay? Since there is no law that says that exergy is conserved, okay, actually because entropy is always generated, this implies that exergy is always destroyed, okay, so I have a destruction term. And, well, when we add all these terms, we get the variation rate of exergy inside our system, okay? So that's the equation, last week's equation, okay? And just to remember 2 points here are signal convention, okay? So Q is positive when heat is flowing into the control volume. This is a convention. If we calculate a negative Q, that means that Q is going out, okay, of the control volume. So this Q is positive when it's going into the control volume, and W is the opposite. It's positive when it's going out of the control volume, okay? So this is a convention. If during our calculations this W becomes negative, that means that the process is actually importing work, consuming electricity, consuming organized energy, okay? So let's apply this to our process, okay? As I said, we want the minimum amount of work. So we're going to consider a adiabatic process. Well, I can always do this. I can isolate. I can put some isolation here in order to avoid any heat transfer, okay? Also, our analysis is in permanent regime, so all variations in time are zero, okay? This is zero for 2 reasons. Well, it's permanent regime, but also let's assume that the frontier here is undeformed. It's not deforming, okay, it's rigid, so this term is zero, okay? Okay, so no heat transfer and permanent regime. Another important consideration is that if I want to calculate the minimum amount of work, I'm going to assume that my process is so good, it's so nicely designed that there is no destruction of exergy. Okay? Is it possible? Yeah, well, if there is internal heat exchange, for instance, this heat exchange must be done at differential temperature differences. Okay, so by construction, I can avoid exergy destruction. So by canceling this term here, I'm going to get the minimum separation work. Okay, so rearranging the expression, okay, W equals actually what gets in the control volume minus what is going out in terms of exergy. Okay. Well, in our analysis, we're going also to neglect all potential terms of exergy, potential, kinetic, and chemical. Next week or next class, we're going to see chemical exergy. That's the subject of next class, okay? So we remain with these terms, and this is the definition of flow exergy, okay? Okay, another consideration is that I'm going to make this analysis for perfect gases, okay? Perfect gases, just to obtain a simple equation. Okay? If the gas is not perfect, no problem. We simply use directly enthalpies, okay? We consider. But being a perfect gas and our process having a constant temperature, this means that enthalpy is zero, okay? There will be no enthalpy variation throughout the process because for an ideal gas, enthalpy depends only on temperature, okay? If the gas is ideal, you can write H equals Cp times temperature, no matter what pressure. It's independent from pressure, okay? So, since our temperature is constant, our enthalpy terms will cancel out each other, okay? Because the temperature is constant, okay? So, those are our assumptions, and let's apply that to our system, okay? So, and let's consider Earth's atmosphere, okay? And, well, I'm already defining some important terms in our nomenclature, okay? So, our process is happening at atmospheric pressure, 1 bar, 25 degrees, and it is a mixture of oxygen and nitrogen, okay? Well, we know that in Earth's atmosphere we have 21% of oxygen and 79% of nitrogen, roughly speaking, okay? Just to have some numbers to play with, okay? YO2 and YN2 actually are concentrations, okay? And yeah, exactly. And these concentrations can be, we're mostly working with molar concentrations, okay? But it can only refer to mass concentrations. It will depend on the situation. Today, it's almost all the time it's molar concentration, okay? So the constitution of what is going into the separation process is defined by these two numbers, YO2, YN2, which we know a priori that it's 21% and 79%, okay? And what we want to do is we want to, let's say, the mixture here, okay, so N2 here, oops, sorry, N2 here is going to be 0. The concentration of N2 on exit 1 is 0, and the concentration of O2 here is 0 at exit 2, okay? Okay, just to define the nomenclature. And another important point, yeah, let me just talk a little bit. I'm going to explain more about the nomenclature that I'm using, not in this slide, but in next slide. Because I'm telling you that the concentrations I'm using the letter Y, but in the formula here you see the letter X, okay? This is why, this is because, well, we're going to have different letters for different places in the process. So the concentration can be defined through the letter Y or through the letter X, okay? It's, well, independent, okay? So anyway, I'm going back one slide here. We got this formula, uh, which enables us to calculate the minimum separation work, okay? So what I'm doing now, we're going to apply this formula, okay? So the formula is here, and we have entering the control volume, we have two mass flow rates, okay? I have one mass flow rate of O2 and another mass flow rate of N2. Mass flow rate or molar flow rate, okay, depending, well, it's indifferent, right now it's indifferent, okay. So the amount of exergy that is entering is the mass or molar flow rate of oxygen times the concentration, the corresponding concentration, okay. If M is a molar flow rate, X is a molar concentration, okay. Okay, so the amount of exergy entering the control volume is the flow rate of oxygen times its concentration plus the flow rate of nitrogen times its concentration. And the same thing exiting the control volume, okay? So here is the index E for enter, okay? And 1 and 2 for the two exits, okay? Just to explain the nomenclature here. Well, since the separation is a perfect separation, a complete separation, if I have, let's say, 2 kilograms per second of O2 entering the control volume, the separation being perfect, I'm going to have 2 kilograms per second of oxygen here, okay? So the mass or molar flow rate is the same for each species, okay? So I can isolate here the MO2 at E is equal to MO2 at 1, okay? So I can isolate this, okay? So, and rearrange the expression. So the minimum amount of work is oxygen's mass flow rate times the variation of exergy, okay, plus flow rate of nitrogen times delta exergy, delta N2 exergy, okay? And we know, we can already figure out if W is positive or negative. Let me ask you a question. Let me see if you're following my reasoning. I was mentioning that, I'm going back a few slides, okay, just to show you. Yeah, before being separated, we have a high level of disorder. After separation, we have low level of disorder, okay? So what do you think that here, the exergy of oxygen entering the system is higher, is greater or smaller than the exergy of oxygen exiting the system, okay? If the level of disorder after separation is lower, entropy is also lower and exergy is greater, okay? So this difference must be less than 0 if it is actually a separation process. Okay, a mixing process is exactly the contrary. So by mixing substances, we could produce work. And you know, especially those that are used with chemistry, if you mix alcohol, ethanol and water, for instance, it will release a certain amount of heat. Okay, and this heat could be used to generate electricity. Okay, so let me continue because, well, this is X and X is exergy, okay, here. And we saw that the component, The enthalpic components we are neglecting because they cancel out. So we keep only T, the part associated with entropy. Okay, so I'm going to replace this simplification into this equation. Okay, and we're going to get this formula here. Okay, so mass flow rate of oxygen times its exergy variation, which we calculate simply by this term here, T0, environment temperature, multiplying SO2 at exit 1 minus SO2 at the entrance of the separation process, okay? And the same thing to nitrogen. Now I'm doing something, I'm dividing the whole expression by the total flow rate of air, okay? This is not argon, this is air, okay? Because it's still in Portuguese. So by dividing the left and the right hand side by the total mass flow rate or molar flow rate, I get these terms. Flow rate of oxygen divided by total flow rate of nitrogen divided by flow rate of air, okay? So, and this is exactly the definition of the concentrations that we had before, okay? So, MO2 divided by total flow rate is O2's concentration, okay? And here, concentration of nitrogen, okay? So, the final expression that we get is very simple, actually. W, the minimum amount of work. Now we have specific work, okay? Kilojoules by mole or by kilogram. Okay, so this is the minimum amount of specific work is equal to the ambient temperature times the concentrations of O2 and nitrogen times the corresponding entropy variation. Okay, since we know that entropy is decreasing because the level of order is increasing, we know this is going to be negative. Okay, so this is the exergy necessary for the disorder level reduction process, which is our separation process. Okay, yeah, and the total entropy of the system is being reduced because we are separating. Okay, and let's try to calculate, but because okay, this formula comes from our exergetic analysis with some simplifications. But now I mentioned that we are working with an ideal gas. So let's try to calculate that because, well, I want to get representative numbers to show you. Okay, so let's calculate how how much these entropies are going to be reduced by the separation process. So I need to look with a magnifying glass what a separation process is. Okay, so take a look here. I have O2 and nitrogen. This is the molar constitution of air. 21% of O2 plus 79% of N2. Okay, so they are mixed, and we say that they are at ambient pressure, 1 bar. Okay. Well, you know, it's a mixture of perfect gases, so each individual gas is, let's say, experimenting different pressures. It's subjected to its partial pressures, okay? So O2, the pressure that O2 is sensing, that O2 molecules is sensing, is not 1 bar, it's only 0.21 bar. That's the pressure, the partial pressure of oxygen. And N2 is subjected to 0.79 bar, okay? And the temperature, it's the same for both gases. Do you have some problem with this, okay, partial pressure, okay? When we separate, what's happening? I'm going back 2 slides. The pressure is going to, the total pressure is going to remain constant, okay? So when we separate, we still have 1 bar, But now I have O2 separated from N2, and O2, now the temperature is the same, but the pressure is not the same. The pressure submitted to O2 is now 1 bar, okay, because it's separated from N2. So actually, oxygen molecules are being compressed from 0.21 to 1 bar, okay, and the same, nitrogen is being compressed from 0.79 to 1 bar, okay. So that's the calculation that we have to do. And it's an isothermal compression process because we said that temperature is going to remain constant. So for O2, for oxygen, what's happening is you can imagine a piston here being pushed by someone or something exerting a force. Okay, so force times this displacement, because I have to put all golden molecules, golden dots on the left side, so I have to push them to the left side, and this force times the corresponding displacement is the separation work associated with the separation of O2, okay? And the same applies to N2, okay? So it's like having an invisible piston here and an invisible little guy that is pushing all nitrogen molecules to the right, and the force here times the corresponding displacement is equal to this separation work, okay? And obviously we're going to add these two works here. Okay, and since they are perfect gases, temperature being constant, its internal energy is going to remain constant, okay, because it's a perfect gas. So the process can be modeled as a isothermal compression, okay, so you can see in the PV diagram, you have, consider this for oxygen, just for simplicity, okay. Oxygen occupies a large volume, V1, okay? It's being pushed to the left, so it's occupying, at the final state, a smaller volume, okay? And the pressure associated with this, the pressure increase associated with this change of volume is, this process is occurring at constant temperature, okay? So it's easy to calculate this, okay? The work is always PdV, okay? Force times displacement, okay? And since it is a natural, a perfect gas, I can use the perfect gas law and write pressure in terms of its temperature, nRT divided by V, okay? And after all integrations, I get W equals nRT times ln of V2 divided by V1. And if I apply again the natural gas law, I get this relation, okay, which I can express in terms of its molar concentration, okay? Here, right here, Y has to be a molar concentration because I'm using the partial law, the partial pressure law, okay? Do you have some problem? Let me just remind this for you, okay? We know that, I'm going to use this left side, the total pressure is the sum of the partial pressures, okay, so partial pressure of O2 plus partial pressure of N2, okay? And each partial pressure I can calculate from the total pressure by multiplying by the corresponding molar concentration, okay? So those are equivalent formulas, those are equivalent formulas that I'm using in this manipulation here, okay? Okay, so let me move. Now we know how to calculate the isothermal compression work, and I was showing that what we have here is an isothermal compression process. So we're going to apply this to our problem. Okay. In applying the first law for this system, okay, and well, the isothermal compression process, T equals constant, okay, I have, because I want to calculate work, okay, so in delta U being 0, because temperature is constant, I get that Q equals W, okay, so when I compress this gas, its temperature is going to increase. It wants to increase, okay? So in order to remain constant, it has to reject heat, okay? Only I'm talking about internal heat exchange, okay? There's no external heat exchange, okay? And we know that the definition of entropy variation, okay, delta S equals Q over T. T is constant, okay? Actually, the correct or more generic formula here, delta S equals integral of del Q over T. Since temperature is constant, okay, we have integral of del Q, which is Q, okay? So by replacing all formulas that we have here, we get that this final important result, delta S is equal to NR times natural logarithm of molar concentration, okay? And we apply this to our formula. If we have, I don't know, N species, nitrogen, oxygen, argon, CO2, and so on, water vapor, for instance, we add everything up and we get this formula here, okay? This is the total entropy reduction associated with the separation of an ideal gases mixture, okay? If I multiply everything and divide by the sum of all molar flow rates, remember, now, since I use this formula here, Y has to be a molar concentration. I don't have the liberty now of using a mass concentration with this form of formula, okay? So if I divide everything by the total molar flow rate, I'm going to get the corresponding concentrations, because NK divided by, let's say, I'm going to use this definition. NK divided by the total molar flow rate, okay, is a molar concentration, okay? Okay, so, in YK, YK. So by doing this, I get our final formula that the specific entropy variation is equal to this, okay, which I can write simply as YK times Ln of YK, okay. So this is a simple deduction which we're going to apply to our process. So I'm just transcribe the formula here, and now we had a few slides back, we had the minimum specific separation work, okay. This formula, I don't know if you remember, it was here, okay. I just transfer that to here, okay. And by calculating each delta S, as we already seen, we get this final formula here, okay. So when we apply this formula, we get the minimum separation work at constant temperature and pressure for an ideal gas, okay. So this is a very interesting formula that's applied to our atmosphere, to our problem. Well, the universal constant here is 8.314, okay. You can see that I'm using mole not mass. Okay, so it's all analysis is based on a molar basis. Okay, times temperature. The ambient temperature 25 degrees. I have to use Kelvin. Okay, so 0.21 is oxygen's concentration, molar concentration. So 0.21 times ln of 0.21 plus 0.79 times ln of 0.79. Okay, I get this final result here. W equals minus 1.274 kilojoules per mole. What this number means? Well, we can convert, just one thing first. We can convert that to on a kilogram basis by multiplying it by the molar mass of air or of atmosphere. Okay, so 1.274 kilojoules per mole or 42.51 kilojoules per kilogram. Okay, this means that if you want to separate oxygen from 1 kilogram of air, okay, you're going to spend 42.51 joules. That's what this number means. Let's see it applied. Okay, so this is the actual composition of atmosphere, 0.21 roughly. Okay, and we get oxygen at 100% concentration here. Okay, so we on the other side, on the other exit here, we have all other components except oxygen. Okay, okay, the other components here can be mixed up, no problem. But by having oxygen at 100% here, I'm going to spend this amount of work here. Okay, but this is, remember, 42.51 kilojoules per kilogram was the minimum amount of work. And this is, well, if the world was perfect, that's what I would spend. But, well, the world is not perfect, so we're going to spend more than 42.51. Okay, 42.51 is the minimum amount of work that theoretically I can spend. Okay, I already mentioned that where this problem is important. Okay, remember the first slide that I showed you was a CCS machine. We want to separate carbon from the atmosphere and store that on the underground, in the underground. Okay, and well, in order to do this, we're going to develop an oxy-fuel combustion process. That means that we're burning biomass with pure oxygen, okay, roughly speaking. Okay, and in order to produce this oxygen, okay, I have to separate it from air. Okay, from air. Just, yeah, I have to separate it from air. So this separation process here is consuming a certain amount of electricity, Exergy, and I know that the minimum amount of electricity that it's going to consume is 42.51 kilojoules per kilogram of air here. Okay, so we already have important numbers here that which help us to figure out if this process is feasible or not. We have already numbers. Okay, let me move on. This is our reference sugarcane production process. Okay, just to show you, just to use these numbers, 42.51 to this overall analysis. I'm sure you remember this slide, what I call a reference sugarcane processing plant or industry. Okay, this is actual numbers. Okay, so it processes 500 tons per hour during 200 days, okay, and it emits 2 tons of CO2. There are some arrows and titles missing here, but this is being 2 tons per hour of CO2 is from fermentation from these vats here, okay, and it's also emitting something around I don't remember, 90 or 100 tons per hour of CO2 when we burn bagasse, okay. So how much would be necessary? And we export 50 megawatts of electricity. If we want to incorporate a oxygen separation process, how much of this electricity we would have to invest, we would have to spend on our separation process, okay? So the calculation is simple, okay? This is the amount of energy exported per, let's say, ton per hour of processing. Okay, so 500 tons, 50 megawatts, 50 times 10 to the third kilowatts, okay, divided by 500 tons per hour, okay, it's here. So I have 360 kilojoules per kilogram, okay. So that's our, let's say, specific electricity production. So I'm comparing 360 kilojoules per kilogram with 42.5. This is the minimum amount of work. It's a very promising number. It's because it's only 15%. Okay. So if the world was perfect, no reversibilities, no exergy destruction, we would only have to spend 50% of our electricity sales, sacrifice only 15% of our electricity revenue in order to separate oxygen. Okay, so just to give you an idea of how this number can be used. This other example here is an actual oxy-fuel combustion process, but not biomass, a pulverized coal. Okay, so coal to generate electricity. It's almost 1 gigawatt. That's the reference paper, okay, if you are interested. And well, the separation process, let me go back 2 slides because my sketch here actually depicts a membrane separation process. I don't know if I can zoom here, okay. It's a membrane separation process. It's a more recent technology, separation technology, and it is very promising in terms of spending smaller amounts of work for the separation process. Traditional separation processes are actually cryogenic processes, okay, such as this one here. You have air, okay, you have, let me zoom this because it's, okay, here. Okay, so you have air input here, it's being compressed, then you cool, and you liquefy. The idea is to liquefy oxygen and nitrogen separately, and then you can separate. So it's a cryogenic process. You separate, you liquefy, then you separate oxygen here. Okay, it goes to the process, to the oxy-fuel process. But before here you have liquid oxygen. Okay, liquid oxygen at high pressure because you compressed here. If you expand liquid oxygen, it's going to, its temperature is going to drop dramatically, okay, minus 160 degrees or something like this. It depends on the pressure. And these cold gases can be used to cool, okay, to cool because when you compress air, it gets hot, okay, so you avoid spending energy, for instance, in this refrigeration process here. But anyway, this is a cryogenic separation process, okay, which separates oxygen for the oxy-fuel process. we know that a perfect process would expend 42 kilojoules per kilogram, and these guys here did some inventory and got this number. This cryogenic separation process is actually consuming 1 order of magnitude higher, okay, 889 kilojoules per kilogram. So that's the point. When I say that if the world was perfect, we would spend only 42. The world is not perfect, and we can consume 20 times more. And well, in this process is actually a very good, high quality process. Yeah.
I have a question.
Go on.
When you use the pure O2, are you avoid to the incomplete burn in the furniture or not?
No, I'm not concerned with this, what I call details, because the idea is just to get these big numbers here. You see that today's technology spends at least 20 times more what would be the minimum amount of energy. So this means that there's a lot to be done, because 42, we can achieve 42, but we are consuming 889. So there's a lot of improvement, room for improvement here. So incomplete combustion, I would say that if you have incomplete combustion, you optimize your burners for instance, in order not to have incomplete combustion. Okay, I'm not sure if I made myself clear. Okay, okay, yeah, okay. Yeah, I'm going to talk about, because I already explained this diagram here for you. Okay, we have we have flue gases here, which are actually, let me get my pen. We have here CO2, O2, and H2O here, because it's an oxy-fuel process. Okay, we cool these gases and we get water here, so we have pure CO2 here. Okay, pure CO2 at low pressure. Okay, so what we do next, we compress in order to get supercritical CO2 here, SCCO2. Okay, supercritical means that pressure is going to be greater than 70 bar, for instance. The temperature, 30, 40 degrees or something like this. Okay, so we're going to compress CO2. The point is, if I'm spending too much work here in order to have pure CO2, pure O2 here, and I know that in practice this number can be 20 times bigger, okay? Is it possible to spend less by allowing a purity of oxygen to fall to 99% or 90% or something like this? Okay, we're going to make this calculation in a few moments. Okay, and the idea is to try to reduce this consumption of work here. Okay, so I'm not considering the quality of the combustion process here, as you mentioned, but I'm considering the quality of the separation process. Okay, we're going to have a less perfect or less complete or incomplete separation, and try to calculate the amount of work involved. Why can we do this? Because when we compress CO2 here, for instance, those are the compressors, okay? I'm compressing CO2. If I have some small amounts of nitrogen in the process, it's going to it's going to pass, and it's not going to liquefy here because the pressure is low for nitrogen to condense itself. Okay, so that's why we have non-condensables being rejected here. So if I allow some amount of nitrogen to go through the process, I have a very good place where to get rid of it. Okay, and this can be advantageous in terms of the amount of work involved in the separation process. Okay, here I also have a separation process, but the energy is gravity here. Okay, it still consumes exergy, but from the exergy associated with the center of gravity of the system. Okay. Yeah, and as I was saying, this is the cryogenic separation technology, which is old and but very, very, very reliable and well, less cheap than membrane gas separation process. This is a new process. It's more efficient in terms of energy use, okay, but it's still very expensive. Has difficulties in terms of scaling it up, okay, and well, there are other technical problems related to membrane separation when we talk about this kind of application that I'm showing, especially the very large scale ones, okay. Yeah, let me see where I'm going. Yeah, so I was mentioning that the whole idea is to sacrifice some amount of electricity, the revenues from selling electricity. This minus delta means that we're going to invest, okay, in the separation process here in order to produce supercritical CO2, as I was showing. But since I have a very nice place where to reject N2, which also can be a product because it has commercial value, okay? The point is, if I let some small amounts of N2 here, okay, so I have CO2, H2O, and N2, okay, but small amounts, okay, and I can reject that prior to sending it to Earth's underground, okay? So the point is, how can we calculate the specific energy associated with a partial separation of oxygen from the atmosphere? So let's see. And as I was saying, we have in our CCS sugarcane plant, we have a place where to reject N2 because it's non-condensable in these conditions, okay? So we have a product of interest, which is O2, okay, entering at a specified input flow rate and concentration, okay? The atmosphere, if this is the atmosphere, we calculated that the minimum separation work for a perfect separation, complete separation, minus 42. This is the theoretical minimum, okay? Now, we don't require 100% concentration of oxygen here, okay? Our product of interest, we will allow it to, well, at its corresponding exit, to flow at a specific flow rate and concentration. Those are parameters that we can play with, okay? And the other exit, all other constituents. So that's the calculation that we're going to do now. And the idea is to get, this is funny because W minimum, we're going to get work which is smaller than the minimum, okay? This may be contradictory, but actually W min is for perfect separation, okay? This W, which is smaller than W min, is for partial separation, okay? And both are theoretical, okay? And perfect in the sense that there is no Exergy destruction, okay? So now I'm going to use a convention here Okay, I need to explain this. The index E stands for the entrance, okay, and the index 1 and 2 stands for output number 1 and output number 2. Okay, so Y1 and 2 is the concentration of nitrogen at exit 1. Okay, I hope there's no problem with this convention here. And as I was saying, the idea is to increase concentration of O2 at, let's say, exit number 1. And since we are increasing concentration of O2 at 1, it will forcibly decrease at exit number 2, okay? Because we know that when we apply a mass balance, Y at the entrance O2 equals Y1 O2 plus Y2 O2. Okay? This is mass balance. Okay? Okay, let's go on. Now we do the same. We apply our exergetic analysis equation. The process is adiabatic, permanent regime, okay? And we want the minimum separation work. So we cancel the destruction of exergy. There is no chemical reaction, no supersonic flow, supersonic shock waves. Okay, so minimum, no exergy destruction. We get the same equation actually. Okay, and we apply this the same way we apply in this case. Okay, so now we get this expression. Okay, exergy entering minus exergy exiting. Okay, we have oxygen entering and nitrogen entering at E. Okay, and now we have oxygen and nitrogen at 1. Okay, at 1, and also oxygen and nitrogen at 2. That's the difference when we compare this with our last analysis for complete separation. Okay. Now, when we replace the equation that we had to calculate the exergy of a perfect gas, okay, we get in terms of its corresponding entropies, and then we can use the corresponding molar concentrations. Okay, so now we have this expression here. I'm just going back a few slides to show the corresponding equation on our first analysis. Was this one, okay? This one here. Okay, so now for many components and partial separation, we get a similar formula, except that, well, we have oxygen and nitrogen at both exits, 1 and 2. Okay, so that's very simple. Okay, and now just nomenclature here. N is Ne, and E is total molar flow rate, total molar flow rate, okay? N2 is, Ne is total molar flow rate at the entrance, okay? And N2 is total molar flow rate at 2, and N1, okay, is the total molar flow rate at exit number 1, okay? Just the nomenclature here. Okay, well, so how things are supposed to work. Let's, before doing some calculations, let's see how this is supposed to work. Let's try to figure this out through the help of what we call operating envelope of the separation process. Okay, so it's a graph. Here we have concentration of O2, for instance. concentration of O2, and here we have molar flow rate. Okay, so if the amount of work injected, let's reason like this, if the amount of work is equal to the minimum separation work, I get what? I get 100% of O2 at 1, at exit number 1, and the input flow rate is equal to the oxygen flow rate at exit number 1, okay? But now I'm not going to inject this amount of work. I'm going to inject a quantity that is smaller, okay? So what I could get is, well, instead of 100%, I could get 99, 98%. I have my concentration becomes small, okay, small, decreases, concentration of O2, consequently the concentration of N2 increases, and well, I also can have a certain concentration, okay, it may decrease to a point that, well, it's going to be 0 on the other side, okay. So this is how qualitatively this graph should work. We're going to calculate today. Actually, I'm going to show you this spreadsheet to calculate this. Okay, it's a very simple problem. Let me just control the time that I have. Okay, so from an operating point of view, let's say that I'm going back some slides. Okay, let's assume that, where do I have this? Yeah, here. Let's assume that, well, I'm going to accept 99% of oxygen, molar concentration, because, well, I can deal with 1% of nitrogen. This separation process works well until 1% of nitrogen, okay? Well, so I'm going to impose oxygen concentration. I'm going to impose a certain amount of injected work smaller than the minimum for complete separation, okay? And the idea is to calculate, okay, if I fix this, I'm going to try to calculate this, okay? So that's our flight plan for the next, I don't know, possibly 45 minutes or something like this. Okay? Just the idea, remember, the idea is always we're trying to reduce this amount of work here because we know that current technologies are very demanding in terms of work, injected work. They are still very far from the theoretical minimum. Okay? Well, so let's see the equations. Okay? So these equations that I'm going to show is for the construction of what I call operational envelope. Okay? So let's think about the problem first before going to the equations. Okay? We have actually, this problem has 15 describing variable or parameters. Okay? Let me get my pointer. 15 describing variables of parameter. Let's count. We have total molar flow rate entering the control volume. We have total molar flow rate at exit number 1, total molar flow rate at exit number 2. Of course, I know that because mass is being conserved, and E equals N1 plus N2. I have all these equations, okay? Okay, so other variables, what I'm calling describing variables or parameters, I have concentrations at E at 1 and 2, okay, YO2 and YN2, and I also have molar flow rates. Okay, so it is obvious that NE is equal, the total molar flow rate at E is equal to molar flow rate of O2 plus molar flow rate of nitrogen. Okay, so I have all these simple equations that we're going to use in addition to the equation of Exergy that we got. Okay, to the equation that calculates for us the minimum amount of work. Okay, so let's move on. Now, I said that we're fixing the concentration of oxygen concentration. Okay, I'm going back 2 slides or 3. What I said, we're going to fix this number because, well, this is a design decision. 99% of oxygen at 1, okay? So we fix this. We also know the amount of air that I have in order to have a certain amount of oxygen for burning a certain amount of fuel. Okay, so this is another design parameter. And, well, the concentration in my, let's say, feedstock, because that's the concentration of oxygen in the air. Okay, so if I count this, I already know from the 15 I already know 5. Okay, so I can eliminate this. Okay, as I was saying, I can also calculate some parameters, because if I know the concentration of oxygen in the air, I can calculate the concentration of nitrogen. Okay, at 1, 2, and 3, at 1 and 2, and at the entrance. Okay, so I have this possibility of calculating several other parameters, and I end up with this problem. I don't know if you see, but I'm highlighting in red the variables that I know a priori, okay? That I don't have to solve a mathematical problem to calculate. So I know all input conditions. This is simple. Concentration of air and nitrogen, and molar flow rate, because this is fixed. This is determined by the amount of fuel that I have to burn, okay? Okay, if I fixed the concentration at the exit of interest, number 1, let's say, I can calculate the corresponding concentration of the other components, okay? So I have to determine what is not in red in this slide, okay? Okay, so I have to solve a number of coupled equations. That's what I'm going to show you right now. What are those equations? So let's see. Well, actually, I don't know if I have time. Yeah, I have time. I'm going to show you 2 methods to solve this problem. A very silly method, a very, let's say, the word is a very widespread. I don't know. 99% of engineers, especially traditional engineers, use this method that we call functional iteration method. Okay, the idea of this method I'm going to show you is to well, if you have a set of equations, let's say 2 equations, so you make an estimation of your variable, for instance, and the idea is to manipulate the equations so that you recalculate the variable that you estimated in the first place. So you can establish a recursive calculation process, exactly like this. Well, this is very, 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 very common process, but it's a terrible process. I think it's the worst process in the world. Okay, so I'm showing it to you because I'm sure you're going to find this process in some books or papers that you're going to read. And I'm also going to show you a very simple method, but a very better one, which is the Newton-Raphson method. Okay, so just very quickly, I'm going to show you this process. Okay, so the idea is to estimate something and calculate the thing that you had estimated. Okay, So let's see how this could work. Let's see our mass balances. Okay, so I know that the total input mass flow, the total molar input flow rate of oxygen, okay, is equal to the molar flow rate at 1 plus molar flow rate at 2. Okay, that's okay. I can write this in terms of its concentration, oxygen's concentration. So NO2 at E is the total molar flow rate times the molar concentration. Okay. Same thing for the flow rate at 1. Okay. Concentration of O2 at 1 times the molar flow rate at 1 and concentration of O2 at exit number 2 times molar flow rate, total molar flow rate at 2. Okay. I already know that Ne equals N1 plus N2, and if I replace that in order to eliminate N2, because I'm interested in N1 actually, okay, so in the place of N2 I write Ne minus N1, and if I divide everything by Ne minus N1, I get this equation here, okay, which we're going to call equation 1. Okay, this is equation 1 in Homer's iteration diagram. Okay, let's see equation 2. Well, equation 2 is our Exergy balance. Okay, so this is equation 2, which we are manipulating in order to recalculate what we're going to estimate in equation 1. So I'm going back to show you equation 1. We're going to estimate this, how much of the input flow rate I'm going to recover at 1, at exit number 1. So 70%, 60%, 50%, I'm going to estimate this number. Okay? So I'm manipulating this Exergy balance equation in order to isolate this term, N1 divided by Ne. Okay? It's simple. You simply pass this term to the left side of the equation and divide everything by this term here in brackets. Okay? So it's very simple. The expression seems very complicated, but the ideas are very simple. Okay? There is really no problem. So this is equation number 2, and I can use this mass balances equation in the place, for instance, because I don't want to work with N2, and I don't want to work with any variable relating to exit number 2. So I use mass balances equations in order to replace the corresponding values with the ones relating to number 1. Okay, so I do this. And, well, we make this iteration process. I think this spreadsheet is here. Let me see. Yeah. No, it's not here. Okay. The spreadsheet's not here. I have the spreadsheet from the other process. So, as I was saying, you make this calculation process. You start by, as I was saying, let's say that we want 40% of oxygen at exit number 1. This number is fixed. Okay, this comes from the engineering department. They said, oh well, 40% is okay. Okay, so if there is 40% of oxygen at exit number 1, there is 60% of nitrogen at exit number 1. So this number is also fixed. Okay, and as I was saying, we start by estimating N1 divided by Ne. Let's say that it's 0.2. So 0.2 is inserted in equation 1. Okay, these are intermediary equations. So if N1 divided by Ne is 0.2, N2 divided by Ne is 0.8. Okay, and the corresponding equations here. And when we replace, okay, this variable here YO2 at exit number 2. When we insert that into equation 2, we get this estimate of N1 divided by NE. And the idea is to replace, to iterate, okay? So this number goes back, this, let me zoom there, okay? Here. So this number here, 0.205843, comes here, 0.205843, and you get 0.2124, 0.2124, you see where it's going. The problem is that this process does not converge, it diverts, okay? So that's not a problem of your solution method, of your iteration, of your equations actually, but it's a problem related to the functional iteration method, okay? So that's terrible actually. And there's a much simpler way of solving this method. I have this spreadsheet. If I look on my laptop, I can find it, but well, I'm going to show you another one. You can try to adapt your equations. Okay, we were working with that particular equation number 1 and that particular equation number 2, but well, you can do differently. Instead of estimated N1 divided by NE, you can estimate the concentration of O2 at exit number 2, okay, and use another form of the same equations in order to calculate N1 divided by NE, and another form of equation, actually the Exergy balance, in order to estimate the variable that you estimated in the first place. Okay, if you change the equations, you may get a method like this, a conversion process like this, okay, which is convergent actually. But the problem is you never know. You never know. There are some mathematical tests to try to figure if the iteration process is going to be convergent or divergent. But these mathematical tests are, let's say, much more complicated than adopting a different solution method, which I'm going to show you now because it's really very simple, okay? It's called the Newton-Raphson method, okay? So I'm going to explain it. Very simple, very simple method. I can explain it to you in this graph here if you pay attention. The method starts with a seed, an estimation of the solution, okay? We have to find the root of an equation, okay? Fx equals 0. So we have Fx here. Its graph is the red line, and the root is the point where f crosses the x-axis, okay? So we want to get to this point here. The iteration method starts like this. You start with an estimate of your variable, x0. Let me zoom there, okay? Okay. So you start by estimating your solution, okay? Then you calculate the value of the function f at this point, f0, okay? Then you calculate the tangent line, okay? And the root of the tangent line, straight line, is your next x, okay? Then you repeat the process. Calculate f1, calculate the tangent straight line, and the root of the straight line is your next x, okay? So it's a very simple method. When you write the corresponding equations, let me get here. When you write the corresponding equations, you get this recursive formula here, okay? For one variable, fx equals 0. If you have a set of equations, okay, you have this adaptation, let's say, of the process. It's also very simple because if you have several variables, what you need to do is to vectorize. So instead of having one single variable, one parameter, you have a vector, okay? A vector here, a vector of functions here, and now we have to, in order to extrapolate this derivative here, now we have the derivative of all functions in terms of all variables. This is the Jacobian matrix, okay? Okay, so it's a crash course on Newton-Raphson method. I don't want to spend a lot of time on this. Let's apply this method because it's very simple, okay? So just to deduce the equations for you, see, you know the mechanics of the method already. So in order to calculate the tangent line, its generic form is y equals a times x plus b, okay? A, since it is the tangent line, it has the same inclination, so the derivative is the same, a equals f prime, okay? Then another information about this straight line is that it passes through this point here, okay? So when I replace x0 in its equation, I get f of x0. From this equation I can calculate parameter b, okay? So the two parameters are here, and that's when I calculate the root of the tangent line, I simply make y equals 0, okay? Then I get this formula here. Okay, so let's apply this to our problem. That's the equation that we have, okay? The one that I modified in order to isolate this term, n1 divided by ne, okay? And by replacing these formulas here, because as I said, I don't want to work with any variable relating to exit number 2, okay? I get an equation, a huge equation actually, but huge but very simple, okay? And I'm going to apply Newton-Raphson method, okay? So this is done in a spreadsheet. This is a tutorial part of the class, so if I have time, I'm going to build a spreadsheet from scratch, and I have time, so we're going to do. But I have already the spreadsheet here, so if I make some mistake, we can I can use this spreadsheet here. Okay, so now I'm not on PowerPoint anymore. Do you manage to see the equations here? Okay, so this is I'm working with Excel. This is our input parameters. So I have, let's say, let's do something here in order to help. Where is my, yeah. Let me get a picture for you guys. Just a minute. Yeah, this one. Okay. Let's get this picture here. Oops. Because it's easier to follow like this. Okay. So I'm going to paste this picture here, and you can better understand here. Let me. Okay. Okay. So this is our separation process, and these are our a priori known parameters. I have, let's say, a total flow rate of 1 mole per second. This is air, okay? Nitrogen plus oxygen. And, well, I just set 25% oxygen. That's the constitution of air at the input, okay? 25%, 75%. We're going to change these numbers, okay? Okay, so those are the a priori known parameters. Okay, this is the amount of work that I am injecting in the separation process. Okay, so it's smaller than the theoretical minimum for perfect separation. So this is another design parameter that I already know. I don't have to calculate. I'm fixing it. Okay, okay, and this number 40% is the amount of oxygen that I want at exit number 1. Okay, so this number is also a known number. I don't have to calculate this one and this one. This one I simply calculate by subtracting 1 from 0.4. Okay, so now starts the Newton-Raphson method here. Okay, so it starts by estimating the variable n1 divided by ne. Okay, that's the unknown that we're going to solve with the help of a Newton-Raphson method. Okay, so I'm estimating that, let's put a round number, 0.05. Okay, okay, so when I do this, let me go back to the presentation. Okay, if I already estimated n1 divided by ne, I can calculate n2 divided by ne, okay, which is here. Okay, 1 minus H2 here is the cell H2, okay, so I have 0.95. Concentration of oxygen at exit number 2 is this formula here. Okay, so the formula is here, implemented in Excel. Okay, then we have concentration of nitrogen at exit number 2. Okay, very simple formula. And then I have my function f, which is this function here. Okay, f of x. So this is f of x. X is n1 divided by ne. Okay. Now what I need to do is to, because in order to implement Newton-Raphson, I need to calculate the derivative of f, which is this monster here, in terms of my function, n1 divided by ne. Okay. It's not very simple because, well, you have this term is very simple. This one is also very simple, but the dependence on n1 divided by ne inside these brackets are a lot more complicated. So we're going to do it numerically. I'm going to use actually a finite difference scheme. Okay, df dx. We're going to estimate this as f x plus epsilon minus f of x divided by epsilon. Okay, epsilon is a small variable. Okay, this is actually this is the definition of derivative. When you make epsilon goes to 0, in the limit it becomes the derivative. Okay, so that's what I'm doing here. Okay, in this, let me just. Okay, so here I have the variable n1 divided by ne plus a disturbance, epsilon. Okay, so H2 plus epsilon. H2 is the cell where I have my estimative. Okay, now I recalculate all variables that depend on n1 divided by ne and recalculate the function. Okay, so this is the function without this disturbance. This is the function with the disturbance. Okay. Now I can calculate the derivative, which is this one minus this one divided by epsilon. Now I have everything, and I can calculate. If I apply this formula here, I can calculate a new estimative for my my variable, my unknown. And this new estimative is here. So I started with 0.05, and the first iteration gave me back 0.05223. What I have to do is to copy this number and to inject it here. So I paste special value, okay? Because if I simply copy paste, I'm copying also the formula, and it's going to give a recursive iteration. It's not going to be able to solve, okay? And well, I'm almost, you see 5223, 5222, copy, paste number, and now it's the same. You see, two iterations already give me the solution near to 0 here. So it's a very simple method to apply, very simple method. That's not the only time that I'm going to show you how to make calculations on a spreadsheet. There will be other opportunities. So today I'm not going to build it from scratch, from zero, because I want to control the time that I'm spending. I have a lot to say still. Okay. So that's our solution method. What we do now, no, that's a copy of the spreadsheet. Okay, we do this for different amounts of work and different amounts of oxygen. Okay, so let me explain how this graph can be obtained. Okay, so I'm varying the amounts of work. So work is minus 003, minus 004, 01, minus 02, 03. Okay, then I start by fixing concentration of oxygen and making the solution. Let me show you that on my spreadsheet. What I'm saying is that, well, I can vary the amount of work. I can vary the amount of work. So let's say 0.5, okay? Then, so what I'm saying is that when I fix a certain amount of work, I'm searching for a solution in one of these constant work lines here, okay? When I fix the amount of the concentration at the exit, so I get 1 point. Okay, then I change the concentration and I get another point. I change the concentration, I get another point, and so on. Then I change the amount of work and repeat the process. Okay. An observation here, the variables are different now because, well, those variables are more appropriate for this type of process. So instead of working in terms of O2 concentration here and O2 concentration and the flow rate concentration, okay, well, this is practice, okay, we work with these two factors, what we call recovery factor, recovery factor, which is the ratio of the flow rate of the product of interest to the input flow rate, okay, and the concentration factor is analogous, okay. Why is this? Because, well, you can have 100% of recovery. You can have all oxygen being diverted to exit number 1, but the concentration is not 100%. Okay, I don't know if, let me explain this another way. Let me make, I'm creating a blank slide here for me to make some drawings, okay? I'm going to explain this better because this is important. This is my separation process, okay? Separation process, it consumes work or exergy. And I have, let's say, I have 1 mole per second plus 2 moles per second. So O2 is 1 mole per second, N2 is 2 moles per second. So air is 3 moles per second. Okay? So this is input. And this is the exit where I want my product of interest. So I can have here, for instance, I can have all oxygen I can have here. I can have it here. So I have 1 mole per second of oxygen at this exit. Okay, this means that there is no oxygen at exit number 2. But, so this is not necessarily a perfect separation, because I can have 1 mole per second of oxygen, which is all the oxygen I have at the input, but I can have, for instance, I can also have 1 mole per second of nitrogen, and of course I have 1 mole per second of nitrogen at 2. Okay, so the concentration is 50%. Okay, so I have 100% of recovery, but I have an enhancement, enrichment that is not total. Okay, is it clear? I can work with these proportions. Okay, so sorry. So as I was saying, I can, let me erase some of these things here. Borracha, I don't have my, it's not, okay, I kept all the remarks I did, so I cannot erase this stuff here. Okay, so this is the operating envelope of the process. Okay, this is the operating envelope, and I hope you understand. I made myself clear how to calculate this envelope. But the point is, oh, I need to erase this. Please give me a minute, because it's very quick. Okay. So this is the operating envelope, and well, you see that if you are at this point corresponds to the minimum separation work for perfect separation, for complete separation. We can really inject less work than the minimum. This is saying like this, it's funny, but it's injecting the minimum work for perfect separation. So if we inject less work than the minimum, we allow for less pure oxygen. Okay, so we have to decide if we want a very pure amount of oxygen, but I'm recovering less oxygen. Okay, that's what I'm trying to explain. I'm trying to explain you this. Let's see. Let me get my pen here. Okay. Okay. Let's assume that we're going to inject this amount of work. This is the amount of work that I can inject to separate oxygen from the atmosphere. Okay. Now let's suppose that, just for the sake of reasoning, that the maximum amount of nitrogen, okay, nitrogen max is I don't know, 1% or a little bit more, 5%. Okay, 5%. So if this is so, well, I can do nothing. This corresponds to 95% of oxygen, and let's say that it's this point. So I have this point here. Okay, but if the amount of nitrogen is not fixed, okay, this means that, or it's not fixed, but there's an interval. Well, I can nitrogen can vary between 0 and 10%. Okay, if you have an interval and you already fixed the amount of work, this means that you have an interval here in order to control your process. Okay, the point is, where is it better to work in terms of overall exergy consumption? Okay, so that's how this type of graph is used. Okay, do you have any doubts about this explanation here? Okay, because I'm moving on. Okay. So as I was saying, yeah, sorry, I'm a little bit. So as I was saying, we can allow for less than 100% of oxygen here, or okay, if having 100% is imperative, okay, is it possible to have 100% of oxygen with less than the minimum amount of work? Yes, it is. Sorry, here you're going to have to. You can have 100% of oxygen, but you're not going to have all oxygen. You're rejecting oxygen to the atmosphere. Okay, so if you want 100% oxygen here at this, let me zoom this. Okay, if you have to have 100% oxygen here with less than the minimum, this means that you're rejecting oxygen to the atmosphere. Also rejecting oxygen to the atmosphere. Okay, so this is how this process or this operating envelope can work. And if you allow for some amount of nitrogen, I already explained, you can reject that through this non-condensables exit here. Okay. Okay. Well, just a quick drawing. This other separation process here, I'm going to draw it here. It's you can think of a tank, okay, and you have CO2 here and a small amount of N2 entering here. CO2 is actually supercritical, so its density is high, so it's very dense, okay. So it's going to, not here, a little bit higher, it's going to accumulate on the top, let's say here. And nitrogen at the conditions for supercritical CO2 is still a gas. So you have nitrogen bubbles here. So you have nitrogen bubbles and nitrogen on the top here and CO2 on the bottom. Okay, so you can reject N2 from the top. This valve does this. Okay, and then you have pure supercritical CO2 here. The separation it's also a separation process, and it also consumes exergy. Okay, but the necessary exergy comes from the gravitational potential of this mixture. Okay, that means that the center of gravity is decreasing. But well, we don't have a problem with this. Okay, so there is no great concern about the amount of energy to separate this process. Another important point, I'm going to use this blank slide to stress this point, is that the amount of necessary exergy for a separation process varies depending on the initial concentration. So if we go back to, I'm going a few slides back, if we go back to the perfect separation equation, by perfect I mean total separation, which is, let me see, this equation here. Okay, yeah, this equation here. For perfect separation, it depends on the variables here. I'm going to improvise an explanation on that blank slide, because that's a very important important point that I want to use to close this class. Okay, let me show you. So if you have the formula was N or T, okay, N K L N D N K, okay. And remember that let's suppose that you have only two components, just to remain simple here. Let's suppose that you have only two components. So you have in oxygen, O2, Ln, sorry for this, Ln G N2 minus, and now I can, instead of writing concentration of nitrogen, I'm going to write 1 minus NO2, because 1 minus NO2 is the concentration of oxygen, times natural logarithm of 1 minus NO2, okay? And so now, this equation shows you the amount of necessary work in terms of one concentration, NO2, okay? NO2. And it varies like this, okay? It varies like this. NO2, W. It varies like this, okay? So this means that, well, if you have 50-50%, that's the most difficult situation for a separation process, okay? If you have 10-90, it's simpler than having 50-50%, okay? And with this information, we can go back to our first slides, and yeah, this one, okay? You can think of this process, because this is a separation process. The separation is taking place inside the harvesting machine. It's a pneumatic separation process, and you spend energy. And the energy for this process comes from the fuel. Okay? So, well, this is not a perfect gas, obviously, but it behaves almost like. I could show you the equations or the correcting factors, but it behaves almost or similarly or analogously to a perfect gas. Okay, so you can reason in terms of a perfect gas, and this process, it's a very rough thinking, let's say, but it's almost 50-50. Okay, you have 50% straw, 50% stalks, so it's a very difficult separation process. Even if everything was perfect, even if the world was perfect, and you know that the world is not. So that's why it would be a lot more sensible to have a stationary separation process, because in a stationary separation process, you could, let's say, try to solve or to palliate problems that leads you to increased energy consumption. Because it's stationary, you have more space for separation. If you embark a separation process on a machine, it has to be small, because, well, you don't have a ship, okay? It's a small machine. So it's a lot more sensible to do a stationary separation. Okay, let me go back to my last slides. I see that I'm almost running out of time, because I forgot to mention at the beginning, I need to end the class a little bit earlier today. Okay, so yeah, I'm already late. Okay, so, well, this is my last slide, actually. Okay, the next week I think next week is holiday, but the following week, next class, we're going to see our last Exergy class. We're going to talk about chemical exergy. Okay, so what we're going to do is it's kind of a separation process, but there are chemical reactions taking place inside the system. Okay, so in this example, we have a certain type of fuel. We are modeling this. This is a generic fuel, hydrocarbon fuel, CaHBOC. Okay, A, B, and C. Well, you can set these numbers to represent ethanol or gasoline or kerosene. Okay, it's going to burn with air, and these are the stoichiometric parameters. Okay, in order to balance this equation. And the same way, we're going to suppose that everything is done at a constant pressure and constant temperature. So it's like a mixing / separation process, okay? Because nitrogen, it's not being separated, but, well, forgot to write down nitrogen. It's not being separated, but its concentration is changing. Molar concentration is changing, okay? So we're going to apply this, the equations that I showed you today to a chemical reactor. Okay? And the question is almost the same. The maximum amount of work. What's the maximum amount of work that I can obtain from a certain amount of fuel? That's the point on chemical exergy. And we're going to use all these equations, okay, to calculate the amount of energy necessary to reconstitute Earth's atmosphere to the one prior to the Industrial Revolution. Okay, so with these 3 classes, I think the subject chemical exergy is well covered. But I want to mention this because last year the students asked me to talk more about exergy. I can do this. If you're interested in this type of analysis, I can show you, I can change some classes that are programmed already. They are in video. You can watch in video in Portuguese, unfortunately. Still in Portuguese, but you can watch. And in the place of these classes, I can talk a little bit more about exergy. Okay? So this was my last slide. And, well, now everything is prepared for our, let's say, most fundamental, most important, and in my opinion, most interesting class on exergy next week. Okay? Does anybody have a doubt? Okay, so as I was saying, I have to end earlier this class today. I have an appointment now. And please excuse me for this, but I managed to cover all the subject. Okay?
Professor,
Yeah, go on.
I just have a quick question, very general. In the slide you are showing of the process to produce fuel and chemicals from the biochemical process.
Oh, the first ones.
Yeah, I think one of the first ones there.
Yeah.
I'm just curious whether in these processes of first and second generation produce ethanol, biogas is also produced. I mean, it's also considered.
Yeah, of course. It is. I don't know, something happened with my PowerPoint. Yeah, it's alive. I think I can show you another slide here. Because you're talking about this one, okay?
Yes.
Yeah, but I'm going to use another one, which is the same, actually. The same ideas are behind. Where is it? Where is it? Yeah, here. Only that I'm going to. You see here, well, the second generation processes here, pretreatment and hydrolysis. And I just showed you, you can ferment vinasse, for instance, here from distillation, and you get methane here. I know some sugar mills that do this, okay? And well, this is an idea. You can have because in this process you need oxygen. So the idea was to use the nutrients here to cultivate microalgae, which will produce oxygen. Okay. So yes, you can have gases here. You can have gases being produced uh, through.
And this is usually done, for example, here in Brazil,
Yeah,
with the production of ethanol.
vinasse fermentation is quite usual. It's not very common. Not all sugar mills have, but some have, some do. Okay. No, I don't know any sugar mill that do this. Okay.
Okay.
This is just an
Teacher,
idea.
but the microalgae is the photosynthesis noise looks like citric glands. If you need the light all the time for produce just O2, because she do a photo respiration, no?
Yeah, but well, you can use some electricity here to generate light in order to cultivate this microalgae. Actually, this is a kind of research that I'm doing here in São Carlos. Yeah, because depending on the species of microalgae, you have different spectra of light that is more interesting for cultivation. So, well, I didn't finish all calculation, but I think it's more profitable in terms of you get sunlight, you convert to electricity, then you convert electricity back to light, but on those specific frequencies that are interesting for the microalgae. You see, so the energies from the frequencies that are not used by the algae, or in this way, the corresponding energies are diverted to the frequencies that they like. Okay. Well, this is not practical yet because there are practical problems that remain to be solved. For instance, the size of this. If you're going to use a pond, for instance, to cultivate this, when you do the calculations, how much hectares you need to have in order to produce the necessary amount of oxygen for the combustion, this area here is going to be greater than the area of sugarcane cultivation. You see? So you need to have very effective photobioreactors in order to avoid this type of problem. Okay?
Okay. Thank you.
Okay. Thank you very much.